gas goes to 30%, and then some frictional loss, transmission, and propeller loss is 15%. So only 40% of fuel energy is used by the engine. Also, there is a thrusting energy. So becoming less as big losses are coming because of the cooling system and exhaust gas. So it only goes to the 40% to the propeller, but also propeller reduced again. Oh, there is a propeller loss, right? So that only 20%, 4% is used from the fuel. So not all the energy that goes into the propeller shaft. Propeller is here, right? Propeller is here. Small fraction to overcome friction in the shaft bearings, friction, water. So that propeller convert torsional energy to thrust. So this one is the arrangement of engine, 2 diesel engine, and gears, and shaft. And this is a gearbox. And also there's a propeller here. Electric. Oh, is it? Electric motor is it? Anyway, and so that how can you reduce the energy loss? So usually as a designer, you need to calculate these kind of efficiency option. So here is the engine, there's a gear and shaft and propeller. Okay. So effective power is coming from towing. The model test gives you effective power. But thrust power is, so PE is after shift, the total resistance, including all the things. So when you towing the ship in the model test, you will get PE. But PT is from just after the propeller, thrust power. And PD is delivered power before the propeller. That's before the propeller. And shaft power is here and on the shaft. And brake power is just behind the engine. So there is a loss, small losses, big losses here, and also big losses after the thrust to PE. So here we have a equation for effective power. There's total resistance, speed, and this is thrust power for thrust force. And delivered power, there is efficiencies, propulsion efficiency and hull efficiency. And there are so many efficiency relations here. So again, the effective horsepower, thrust power, delivered power, shaft power, and brake power. Already explained by Sam. So that once again, only I will explain about this. If effective power in the calm water, no wave water, the power required to move the ship at a given speed in the absence of propulsion. So this is a model test, towing tank. You get this effective power. The other one is coming the equation. So that the brake horsepower is just behind the engine, and reduction goes to the effective horsepower. But towing tank, you get this one. As a designer, you need to calculate engine power size. So all the equations need to be calculated to select engine. Electric horsepower can be calculated by delivered horsepower, the efficiency, hull efficiency, and complicated one also water efficiency, propeller efficiency, and wake fraction. Wake fraction is something like this. Wake, I don't know whether there is a picture. No. Wake looks like this one. When the ship, see the ship behind ship. Ship looks like this one. And there is a shaft, and then propellant looks like this one. Right? And the water flow, water is flowing from the front tire toward the end. The water is flowing this way. How do you? But because of the ship is narrow in the end, water is going in this direction, not straight line. That's why the speed around the propeller rotation speed is different. Speed of this area is slow, and this area is high, right? Because of the Hall effect, speed of the water near the top head of the above part of the propeller is low, speed is low. We call this is a wake zone or wake fraction. And because of this difference, the cavitation is coming. Because propeller is rotating, but speed, water speed is different. Only 1 ton of rotation, low speed, high speed, low speed, high speed change. And RPM is something like 100 times per minute. So 2 times per second. The rotational speed is very high. That's why the cavitation can be. All right, so engine selection procedure. How can I select my ship's engine as a designer? So from you can make power requirement by using effective horsepower with starting point, and that is calculated or CFD or model test. Model test can give you effective horsepower, including frictional surface, wave making, residual resistance, appendage, anti resistance, and something else. Many items, small items. And then you can calculate efficiencies and then arrive at rating horsepower just before the engine, rating horsepower. And finally, you can add a C margin because of the C is rough. And also, we cannot estimate something uncertainties. But typically, it is like a big 20% of margin for the engine. So that select the engine for the manufacturers catalog. So as a designer is and submarine bodies, the submarine, the pressure is high at the front and also again high in the end because the speed of the water is moving faster in this region. So there is no wave making, right? Because submarine is below, no wave is making. So only viscous resistance or friction. But for surface ships, the wave is generated. So we call this wave making resistance. Ship moving on the water surface, resistance force comparing to the submerged by the submarine. There is because of the free surface means water and air. Between that is a free surface. There is a wave making resistance. Because this of the gravity and energy losses come. We call this a Kelvin wave. So that again, there is so many energy losses. The friction, shaft bearing. This is the engine, BHP, braking horsepower, shaft horsepower, delivered horsepower, thrust horsepower, and then effective horsepower. Say again, say. Drive, we call this a drivetrain system. Then losses coming from gear, bearing, and sealing, and strut, and screw. So 70% wake is something like this one, weight gain, and thrust reduction. There are so many items. Right? Can I finish up or even time or? Oh, there's many more. We can stop around here. Right? Any questions? And two more pages, then we can finish it. All right. So 2 more slides, then I can finish. So most challenging responsibility of an engineer as a naval architect is selecting an engine, right? As I said. And this is a guarantee speed. There's a contract with the owner. Owner provide a shipbuilding company big money to buy a ship. And usually the contract signed. Main items are delivery date, speed, and cargo capacity. Most important. The speed guarantee is most important. If contract signed at 25 knot speed, but the final result can be 24 knot, then you need to have a penalty money, big money. That's why as a designer, it is important. So how can we calculate? We already see horsepower, watt, and engine output, things like this. And also there is a engine is direct drive is we'll see there's propeller. Right? So this is a engine catalog. Same as your car automotive engine, but it's bigger. Marine engine market size, global marine engine market size, US $1 billion, something like that, and then bulk carriers 40%, Asia Pacific marine engine market, 5 billion, something like that. Anyway, we need to have many engine makers, not shown here. So you can see more items from these slide set or website to get more ideas on choosing a main engine for your ship, torque. All right? End of my slides. Right? No question? Then you can see answers. Right? Thank you. Thank you.